Section 16.2, periodic waves. Periodic waves consist of cycles or patterns that are produced over and over again by the source. So they're similar to the waves we saw before, but before we said it was still a wave even if it was just a single disturbance, a single wiggle that traveled along. Periodic means that you need to create a consistent pattern. So instead of just creating one disturbance as shown at the top, we imagine the hand continues to wiggle up and down or forward and back and create that same pattern again and again. And that's how we can create, instead of just having one disturbance of like an up down in the top figure, we can have an up and a down and up and a down, right? Which starts to look a bit like a sine wave. It looks sinusoidal. That gets us thinking about simple harmonic motion, perhaps, right? It turns out that every segment of the slinky will vibrate in simple harmonic motion if the end of the slinky is moved in simple harmonic motion. So as long as you're moving your hand up and down, similar to the mass on the end of a spring, right? Then you will create a simple harmonic motion pattern throughout the slinky. And this is easiest to see perhaps in the transverse wave, in the periodic up and down motion. It also applies, though, to the longitudinal wave, where it's forward and back compressions. As long as you're moving forward and back, similar to the mass on the spring, you will create these patterns of compression and stretching that still follow for every little particle. It's moving forward and back with that simple harmonic motion. So we see simple harmonic motion feeds right into waves here. We're going to look at two different graphs that will help us to understand this. It's important to understand the distinction between the two. So let's take a look. All right, these two graphs look identical, but the key is what's being plotted here, right? One of them is being plotted as a function of distance, while the other is being plotted as a function of time. What does that mean? Well, that means that the vertical scale is also slightly different. On the vertical scale here, we have the vertical position of the slinky for the first one. The second one is the vertical position on one point of the slinky. What does this mean? Well, for A, it's looking at one particular time as time passes. You can think of it as a snapshot, right? Where if we took a picture of the wave, this is what it would look like. We can see every single location at one particular instant. We'd know that, okay, at this point, it's up in the air. At another particular location, the wave is down, right? But it's all at one particular fixed time. For the second case, it's a plot of the wave at a particular location as time passes. So that particular location is following simple harmonic motion, which is this sinusoidal path. And that can be seen perhaps in this nice GIF that shows that as the wave is moving to the right here, the blue bead is just going up and down, or really it's just a blue dot. It's not even fixed to the vertical axis, but it looks like it is because it's just going up and down as the wave passes through it. And the up and down pattern of this is, if we looked as time passes, we'd see that it follows the sinusoidal path if we stretched it out over time. So there's no way we can capture a picture of this. We would just have to collect the data, like a whole bunch of series of pictures, and be like, okay, at this instant it's right here, at this instant it's lower, at this instant it's lower, and we could slowly plot this out as a function of time passing. Right, so first I really wanted to highlight the difference between those two. And now we'll start talking a little bit more about all the different things that can be shown in these graphs. So in the drawing, one cycle is shaded in color. And notice one cycle is different for each of them, right? Depending on if you're plotting distance or time. We'll get more into that in a moment. But a cycle is a full going through all types of motion. So if we start at the 0 point it's going up, it's going back to the 0 point, but then also going down again before we get back to the 0 point. So it needs to cover all the different things that can be shown. Amplitude A is the maximum excursion of a particle of the medium from the particle's undisturbed position. That's what's shown here towards the end. So it's the maximum distance from equilibrium. That is our amplitude. And notice you can do it on the positive side. You can also do it on the negative side because it's just a distance. The sign doesn't matter. In both cases, it will be a positive A. The wavelength, then, is the horizontal length of one cycle of the wave. So the wavelength is measured when we are looking at distance over here. So we have distance, and because we are looking at a function of distance at our snapshot picture of this, if we measure one full cycle, that will give us our wavelength. And our symbol for wavelength is the Greek letter lambda, which is like a little hut or something, or a chair, or I don't know what you want to call it. But I draw it something like this. It's like an upside down Y. So that's known as the Greek letter lambda. That's our wavelength symbol. The period is the same idea as wavelength, but having to do with time instead of distance. So if we instead look at a plot of the position of one point as a function of time, then if we look at one complete cycle, that will give us our period. And period we've seen before, it has the letter capital T. So because it's a capital T, that indicates there's the time for one complete cycle. It's not a lowercase t. Finally, frequency is related to the period, and it just has the units of inverse period, inverse seconds, which are also called hertz. So either of these work for frequency, and frequency, as before, is 1 over the period. Right, so once you can determine the period, you can then determine the frequency, and you're in good shape there. Now, what we ultimately want to do is connect some of these ideas to speed, right? How fast is that wave moving? So to do that, we're going to think about a slightly different scenario, and that's of a freight train that's passing, right? You get stuck at a railroad crossing, watching the train car go by. Maybe you start counting how many cars there are. I've gotten close to 100 on that, so challenge you to try it sometime. But what if you want to figure out how fast the train is going? Well, you don't necessarily know the total length unless you're really good at counting all the cars and you were there from the start to the finish. But if you just miss one, you're going to be off. But another way you could do it is if you know the approximate length of one of these train cars, right? One of the freight cars. So if we know that length, which we could call x, then we could say x is about 18 meters, which is a reasonable size. Then what we could do is we could use a stopwatch and time how long it takes that one car with a known distance to pass us, right? So if we time that, and maybe we find it's just over 2 seconds, say 2.25. But once we have this known distance with the time it takes that distance to pass by, we can figure out the speed. We know speed is just distance over time. And so we could plug in our 18 meters divided by our 2.25 seconds, and we'd find that that comes out to about 8 meters per second, which is about 18 miles per hour, which is pretty reasonable for the speed of a freight train. They don't tend to be super fast, but they just keep going. So turns out it's a similar idea with waves. If we imagine that instead of talking about it being a car length, right, of a boxcar, we say that that is the length of one cycle, and that this is a periodic train, so there are many cycles. So we call that the wavelength lambda. And the time it takes for that one cycle to occur is our period, t. So instead of x over little t, RV can be calculated with lambda over big T. And similarly, because we know that frequency is equal to 1 over a period, we could write it instead as 1 over t times lambda. 1 over t is just frequency, so we could write the speed as frequency times the wavelength. This is a key equation that defines any wave. For any wave you see out there, it's going to have this relationship. That, for instance, as the frequency goes higher, the wavelength will go lower if the speed stays constant. So this is one of those equations that will allow you to go back and forth between a number of different parameters. It's a really useful one. Let's see how useful it can be in an example. So example 1, the wavelengths of radio waves. AM and FM radio waves are transverse waves consisting of electric and magnetic field disturbances traveling at a speed of 3.00 times 10 to the 8 meters per second. Turns out that is the speed of light because radio waves are an example of light. That's something that comes in physics 2B. A station broadcasts AM radio waves whose frequency is 1230 times 10 to the third hertz, and an FM radio wave whose frequency is 91.9 times 10 to the 6 hertz. Find the distance between adjacent crests in each wave. Incidentally, these are very real frequencies for radios. So AM stations are all in units of kilohertz, that's the 10 to the third hertz, versus FM are a different frequency spectrum. They're at megahertz, 10 to the 6 hertz. So when you tune your radio to 91.9, because you want to listen to Pebble Beach radio, you're actually tuning it to 91.9 times 10 to the 6 hertz. It's a very specific frequency, which is pretty cool. All right, but we want to find the distance between the crests in each wave. So the key first is to figure out what we know, and we have these hertz. The units clue us in here that the hertz are giving us the frequency. Then we also have this 3 times 10 to the 8 meters per second, and that is our speed. So we have speed, we have frequency. What's the distance between adjacent crests? Well, remember our distance for each cycle, if you imagine a nice transverse wave here. So between adjacent crests, that's referring from crest to crest is from high peak to high peak, right? Skipping a lower one. That's just exactly one wavelength. So if we can find the wavelength, we will have the answer to our scenario. And we already know that the speed of the wave is equal to the frequency times the wavelength. So if we divide both sides by the frequency, then we'd have that the wavelength is equal to the speed of the wave divided by the frequency. All right, so let's try it out with some of those numbers then. All right, so lambda is equal to V over F. For the AM, we have the 3 times 10 to the 8 meters per second divided by its frequency. The FM, the only thing that changes is the frequency. Both radio waves travel at the same speed. And as a result, the wavelength is different. For the AM, it's 244 meters, versus for the FM, the distance between the crests, or the wavelength, is 3.26 meters. It's a much smaller wavelength. And that's one of the reasons AM and FM radio stations have some really different, interesting effects. AM radio stations are often able to travel further because of this longer wavelength. They don't diffract as much, but diffraction is another topic. This introduces the idea, though, of how we can go back and forth between a wave's speed, frequency, and wavelength. Those three are all interconnected as long as we are talking about periodic waves. We'll talk more about the speed of a wave in the next section, so you'll want to stick around.